Here I am in Kansas City, where it's cold and windy. And what I have behind me is the philosophy department of the University of Missouri. And I'm gonna run inside to see if I can find Susanna Reinhardt.
Augustine, hey. Surprise! Please
So good to
come
see
in.
you. Thank you. So, what are you up to?
I was opening my mail. Do you want to check it out?
Sure.
All right. Dogs test results. Oh, good. Negative. Uh-oh. Positive for canine plumia.
Oh, wait, but how accurate is the test?
All right, that's a good question. Oh man, the test looks pretty accurate. Let's see. Of the dogs that have the disease, 90% test positive. And of the dogs that don't have the disease, only 10% test positive. So,
oh dear, I mean, that sounds pretty bad. I mean, I hate to say this, but I think he has the disease.
well, I'm not so sure. Don't forget about the base rate fallacy. It says here the disease is quite rare. So only 100 out of 10,000 dogs actually has the disease.
Wait, but if the test is 90% accurate, I mean, he's got to have the disease.
That's what you would think, but if the disease is rare enough, that can make the difference. It can actually be more likely that he doesn't have the disease, even if he tested positive, if the initial probability of his having the disease is sufficiently low.
Wait, you need to explain this.
All right, you want to look at the numbers?
Yeah.
Okay, let's do it. So, Augustine, I'm worried about my dog because he tested positive for canine plumia. Now, we've seen that the base rate for the test is approximately 100 out of every 10,000 dogs has the disease. So that means if we started with about 10,000 dogs, then we expect about 100 to have the disease. And then the other 9,900 would not have the disease. Okay, and we ascertained earlier that of the 100 with the disease, 90% would test positive. So that's about 90 dogs of the ones with the disease that test positive. Now, of the dogs without the disease, only 10% test positive. But still, 10% of that number is still 990 testing positive. So now the thing to notice is that we have a total of 1,080 dogs testing positive, but of those 1,080, the vast majority, 990 of them, actually come from the group that don't have the disease. So because the disease is so rare to begin with, even though the test is pretty accurate, the chances that my dog is in this group, the false positive group, is still 92%.
Susanna, that's amazing!
So, shall we see what else I've got in my mail?
Sure.
All right, let's look at the next letter. Oh, look, this is from my students Candace and Ron. They both want me to write letters of recommendation for their internships this summer.
Oh dear, which one is better?
Well, honestly, between you and me, Candace is quite clearly the better student. Yeah. But look, this is surprising. I'm looking at their transcripts, and it looks like Ron's overall GPA is higher than Candace's.
Oh, really?
Yeah, and let's see, they've both taken only philosophy and English classes. Mm-hmm. And gosh, Candace's GPA in philosophy is higher than Ron's GPA in philosophy. And Candace's GPA in English is higher than Ron's GPA in English.
Wait, so the only classes they took are philosophy classes and English classes?
That's right.
And what you're saying is that Candace did better on average in her philosophy classes?
That's right.
And she did better on average in her English classes?
That's right.
But overall?
Overall, her GPA is worse.
What? There must be a mistake.
No. Shall we look at the math?
Yeah, let's look at the math.
All right, I'll show you. So I noticed earlier that Candace has a lower overall GPA than Ron does. Her overall GPA is 3.1, and Ron's overall GPA is 3.4. Now, this is very surprising because in philosophy, Candace's overall philosophy GPA was 3.0, and Ron's overall philosophy GPA was lower at 2.5. Moreover, in English, Candace's overall English GPA was 4.0, and Ron's overall English GPA was lower at 3.5. How can this be that they've only taken philosophy and English classes? In philosophy, Candace has done better than Ron. In English, Candace has done better than Ron, and yet overall, Candace does worse than Ron. Well, the thing to notice, the way this is possible, is that philosophy is a harder subject overall, and Candace has taken more of the harder subjects than Ron has. So Candace, it turns out, has taken 9 philosophy classes and only 1 English class. Ron, on the other hand, has taken more of the easier classes. He's gone for 9 English classes and only 1 philosophy class. So let's run through the numbers. So Candace got a 3.0 in each of the 9 philosophy classes that she took. So we'll multiply those up, that's 27. And then go ahead and add her English grade. That was 1 English class, so we'll add 4 to 27, and that gives us 31. Then dividing by the 10 classes that she took, that gives us an overall GPA of 3.1. Now let's do Ron. So he's only taken 1 of these hard philosophy classes. He did worse, he got a 2.5, but he's taken 9 of the English classes, so his 3.5 that he got in each of those 9 classes times 9 gives us 31.5. And then adding his 1 philosophy class, 31.5 plus 2.5 gives us 34. And then again dividing by 10 to reflect the 10 classes that he took gives us an overall GPA for Ron of 3.4. So the magic of Simpson's paradox is that within each of these 2 natural subgroups, Candace does better than Ron, and yet overall, Candace does worse.
That was really remarkable. Sometimes things are just not as they appear. Sometimes you do the math and you get a result that is entirely unexpected. So, you must do the math. So what else is new?
Well, I'm trying to set a date for a surprise exam I want to give my students sometime next week. And I announced last week that there's going to be an exam sometime next week, but I want to set the date for myself, just so for planning purposes. And I was thinking maybe I'd do it on Friday, at the end of the week. But then I realized, from the student's perspective, if they get to Thursday night and there hasn't been an exam yet, they know there's one sometime that week. They're going to figure out that it's going to be on Friday, and then it won't be a surprise. And I really want it to be a surprise.
That's right. Yeah.
So I think I have to cross off Friday on my little chart here.
Shall I just cross it off?
Yes, please do. Please do.
All right.
Yeah.
So no Friday?
No Friday. So I'm thinking probably Thursday would be a good day, you think?
Wait. I think if I was one of your students, and it's the night before Thursday, I would say, I know it's not going to be on Friday.
Right, yeah.
Because if it wasn't Friday, it would be a surprise.
Right, because they can go through the reasoning we just went through, right?
So then they would figure out that it's going to be on Thursday. So then it wouldn't be a surprise.
Huh. Well, I guess we better cross off Thursday, too.
All right.
But the same reasoning is going to apply to Wednesday, because the students can go through that reasoning. They know it's not going to be on Thursday for the reasons we just gave. So if it comes to Tuesday night, there hasn't been an exam, they're going to know it's...
That's
I guess
right,
we better cross off Wednesday and just keep going. I mean, the same reasoning is going to apply.
But wait, that means that it's impossible to set a surprise exam.
It seems that way, but, when I was a student, I had exams that were surprises, and they sure surprised me.
That's right. How did our teachers do it?
That's a real puzzle. How could it work?
What's going on?